Yeah, welcome everyone for today's talk. It's a pleasure to have Professor D. Yogeshwaran from ISI Bangalore, and he will be talking on the edge ideals of Erdos-Renyi random graphs. Yeah, over to you.
Okay. Okay, thanks Anurag, and thanks to Anurag, Suchita, and Samir for organizing this very nice series for quite some time. And yeah, it's really a nice initiative, and I attended a couple. Unfortunately, I couldn't attend more, and I have enjoyed it. Thanks again, and for also arranging it in a way that with some date changes and to ensure that me and Arindam speak back to back. This was at least, we thought this would be helpful for people who want to understand a lot of stuff, or we thought it would be good. One of us can give algebraic perspective, other gives a more probabilistic viewpoint. So as Arindam mentioned yesterday, so this is a joint work with Arindam, and so I'll be speaking about edge ideals, but of random graphs. I will try to define many of it. And okay, so anyway, you can see this is of course Arindam. Doesn't look like what you saw yesterday, but nevertheless is the best I could see on the internet. Okay, first important, very important disclaimer is the following. Okay, I'm not really, I don't understand. I just said to the organizers, okay, sorry for disappointing that I'm not really so much of a combinatorial or a commutative algebra person. So there are a lot of things even in this. In general, one doesn't understand many things from one's own research, but in this case, it's a lot more than usual for me. So there are many things I still don't understand completely. So I tried to hope to convey some ideas, some very simple ideas we had, and it was still, I mean, since the subject is still in its infancy, we were able to prove some results which we hope will trigger interest of people in the subject. Okay. And so, okay, what do we do? Let's get to something. So as as Arindam said, the point is, well, he's been dealing with commutative algebra and combinatorics, the intersections of the two. Okay, how do you generate monomial ideals or so using some combinatorial structures? And then this is often very useful in helping to prove, understand certain classes of monomial ideals very well. And so what we thought was that when he visited ISI at some point of time, when he visited ISI, what was a good thing was that he spoke about this work, and what struck me immediately, or any probabilist for that matter, this is a well-established phenomenon in probability, is that whenever you are studying a class of objects, it's often very useful to, it goes back to Erdos and Renyi themselves. They introduced random graphs, Erdos and Renyi, precisely to study properties of graphs. Okay, you couldn't study a class of graphs. It is not very easy at all. Okay, sometimes it's very complicated. So they just looked at properties of random graphs and were able to prove interesting things. That if you ask me to prove a property of a class of graphs, it seems very hard. But you pick out a random member from that class of graphs, you are able to say much more. Okay, so this is what drove Erdos-Renyi. They were able to do many things, and this is what immediately led me to ask Arindam that, you know, you're showing all these things about edge ideals of graphs and various interesting properties. Now, what if you take it to be random? What are the things one can say? Is there anything known? So at that time, I mean, this was nearly 3 years ago. So it took us some time to warm up to each other's subjects and, understand, even to figure out a common, it's often, even though people think mathematics as one whole subject, It's even between same subjects, it's sometimes a problem for mathematician to discuss, but across subjects, it's sometimes even more. Anyway, in the meanwhile, before us, there's some other people, but the time we started, hardly there was anything 3 years ago on random edge ideals, random monomial ideals, maybe one, maybe two papers, but now probably already there is a dozen. Okay. Um, so here is a basic setup. So this is just briefly recollecting Arindam's notions and so on. So Arindam's slides, I think, are already available on the website. So somebody wants to quickly run over, it's useful if you can keep it and check some things if there is some doubt. But let me run over, at least I will try to keep it self-contained. There'll be some things not clear. So I take a simple graph G, and always I assume my vertex set to be 1 to n, and E is my edge set. Okay. And edge ideal to me is that nothing but corresponding to each of the vertices, you associate a variable to each vertex, and you take pairs of variables corresponding to edges, and you generate an ideal. Okay. And it's an ideal in the polynomial ring on n variables. Okay. So n is the number of vertices, and you take square free, you generate with degree 2 generators. Okay. Square free degree 2 generators. So whenever ij is an edge, xij, xi, xj is the generator for your ideal. And so you consider, you generate square free monomial ideals with degree 2 generators. Okay. And as Arindam pointed out, you can put them in one-to-one correspondence with finite simple graphs. Okay. So given a finite simple graph, I've told you how to generate an edge ideal now with degree 2 generators. And so whenever all edge ideals, you can associate a finite simple graph. It's straightforward, one way and the other. And there are three important notions for us. There is a fourth one, I'll come depending on time. The three important notions for us is, as Arindam introduced, one is what is called linear resolution of an edge ideal. And this is stronger than what is called linear presentation. So as Arindam pointed out, again, resolution means that given an ideal, I can come up with a sequence of exact maps. Okay, decomposing the ideal, I can come up with a sequence of exact maps, finitely many of them. Okay, and linear resolution somehow says that all those maps are linear. Linear presentation means one of the first maps is alone linear. Okay, these are, so as I said, I still don't fully appreciate the usefulness or so on, but well, I trust Arindam and I trust many other people who work in this subject. There is something important about having these kind of things to be linear. Okay, it tells you more. And linear resolution often is also equivalent to saying regularity, which I denote by reg, which is also the Castelnuovo-Mumford regularity. This is the only regularity I know, but people in the subject, of course, have ideas of other notions of regularity, I guess. And regularity has to be equal to the d, where d is the degree of the generator. And in this case, we are dealing with edge ideal. These are concepts which are true for any monomial ideal. But in the case of what is specific to the case of edge ideal is this factor 2. In a general monomial ideal, it has to be d, where d is the degree of the generator of the monomial ideal. Okay. So because we are dealing with edge ideals, degree is 2. Okay. So this is primarily all that you need to know on the combinatorial, on the commutative algebra side. I will rephrase all this in terms I needed or what is useful. So, and you can immediately see why it was possible for me firstly to even contribute anything. Because, okay, I didn't have to deal with so much algebra. Arindam helped me to, or showed me how you can reduce it to combinatorics, or how people have reduced it to pure combinatorics. But that is also what we have got. Okay, already I see a question. What about the case when monomials generators have different degrees? Okay. So to Gargi's question, I will make a small quick point to that a little later. But we don't deal with this, but this is something that would be a possible future someone should, definitely this should be considered. Okay. Okay. Arindam has already said the implication is okay only for monomials if the generators are the same degree. Okay, and there's a very nice survey, but Adam Van Tuyl, okay, which is sort of where I picked some things up from, or I understood some things. Okay, there are of course books as well on the overall commutative algebra part or monomial ideals and stuff like that, but purely on edge ideals, there is a survey by Adam Van Tuyl, highly useful if you want to at least understand some things. Okay, so let's go on. I will now introduce some combinatorial notions. Okay, so G complement to me is the complement of a graph where the vertex set remains the same, but the edge set is the complement of the edges. So it's essentially you whatever edges were there in the graph, you delete them and put those edges which were not present. Okay, and now the important thing for us is a cycle. So cycle, K cycle is a standard notion, all of you know. A chord in a cycle is an edge between two non-adjacent pair of vertices originally in the cycle. Okay. So I've represented it geometrically. I'm not saying it very specifically. Okay. A chord is for me, a chord in a cycle means that there is an edge between, a cycle has an ordering and an edge between two non-adjacent vertices in the ordering. Okay. So this is what is a chord for me in a cycle. I call a graph to be chordal if every cycle of length greater than or equal to 4 has a chord. That is, if I give you any cycle like this of length k being greater than or equal to 4, okay, there should be a chord. This is a chord for me. So there is an edge between non-successive vertices. Okay. So this is what I call as a chord. And of course, cycle of length 3, you cannot have a chord. Okay. There is no way. There are no non-successive vertices, so it's trivially okay. Okay. So co-chordal means that the complement is chordal. And similarly, I define what is 4-chordal is that if every cycle of length 4 has a chord, okay, if every cycle of length 4 has a chord, and similarly, you can define 4 co-chordal. That is, you don't ask chordality for cycles of all lengths, but only length 4. So there is some special thing to this. 4 chordal and 4, similarly 4 co-chordal, okay, which means that the complement is 4 chordal. 4 co-chordal means that the complement is 4 chordal. Okay. Why do I care about this? Here is a very easy thing now, beautiful thing that tells me Froberg's theorems. Okay, I say, well, it's not one of them is Froberg theorem, as Arindam said. The other is okay, sort of folklore, but not clear. I'll just simplify this. Is that linear resolution is equivalent to co-chordality. Linear presentation, which is weaker, is equivalent to 4 co-chordality. Okay, so in the first diagram I presented, linear resolution implies linear presentation. You might wonder, is the converse true? Now, Froberg's theorem gives an easy way for even a combinatorics person. Well, you don't need to be really a serious combinatorics person to realize that this implication does not hold always. Okay, so linear presentation need not imply linear resolution. So Froberg's theorem is, well, that's the easiest consequence of things, but it's a much more powerful thing because it characterizes something very algebraic in something very combinatorial. Okay, very, very easy to understand. And now what about linear presentation is in fact even better. You understand it in terms of 4 co-chordality. 4 co-chordality is very local thing because you have to look only at 4 cycles everywhere. Arbitrary cycles maybe is very big, you do not know, maybe you have a cycle of very large length in a graph, but four cycles are easy. You can run through all possible four cycles and check for things. You will see this in our proofs. And precisely this is what Arindam told me when I first spoke to him. This is exactly he told me that there is this thing for co-chordal and there is co-chordal. Okay, I said this should be studied. You can do it for random graphs. Not a big deal. It should be doable. Okay, it was just I mean, if you have worked with random graphs, any person who has worked even some of my master student, I would expect them to guess this part. Okay. Now, conjecture by Nevo and Piva, what Arindam said, linear presentation does not imply linear resolution. But what they said is if you have linear presentation and regularity is less than equal to 3, regularity 2 means it's linear resolution. All higher powers have linear resolution. That's not a big deal. But regularity less than equal to 3 means some higher power will have a linear, all higher powers. So regularity 2 means this is trivially true with s greater than or equal to 1. Regularity 3, it's saying from 2 onwards, it has linear resolution. Okay. So this is Nevo-Piva conjecture that linear presentation alone is not enough to guarantee linear resolution, but you need something more to guarantee all higher powers at least have linear resolution. He said it's some versions, well, he presented yesterday, but not everything. There are still some missing things here. Okay, the conjecture, of course, is still open. And what my first guess and what we showed is that, well, in probabilistic term, this conjecture is more or less redundant in the sense that what I told Arindam first time and what got us excited is for random graphs, whenever you have four co-chordality, you should get chordality. That is, this implication has to be true. Okay, that's what we showed for random graphs, that this implication is true for random graphs. Okay, so what we had is that what we show our first result for random graphs, I will define random graphs, is 4 co-chordal implies co-chordal for most random graphs. This is the key point, most random graphs. There is always a parametric choice for random graphs, often. So for most choices of the parameters, it is true, the statement. Okay. And if co-chordality is true, regularity is true, that is, you have linear resolution, and all powers have linear resolution. This is what Arindam also said yesterday. If Ig has linear resolution, all higher powers have linear resolution. So what we are seeing in Nevo and Piva conjecture, what we are saying is probabilistically, this is not needed. This is not needed. Okay. And this one, I can take S to be greater than or equal to 1 itself. This is what we are seeing in Nevo-Piva conjecture, what random graphs help us tell us. Okay. That is, you pick a graph at random, very large, asymptotically. These are statements for very large random graphs. So you among graphs on n vertices as n goes to infinity, I'm saying that you pick a graph at random among all possible graphs on n vertices. You check whether it is 4 co-chordal. This is reasonable to check. If this is true, it is highly unlikely the graph is not co-chordal. Okay, we will tell you something more. Our actual statements are much more precise. They'll tell you the exact probabilities to everything in all reasonable cases. Okay. Okay, so let's say what are random graphs. Okay. So ER stands for Erdos-Renyi. It's now nearly 60 years old. Okay. So G, N, comma, P is my notation for a Erdos-Renyi random graph. It has two parameters. N is the set of vertices, always. And my H set has a probability P associated with it. Okay, P is a probability. So let me put it. Yeah. P belongs to 0, comma 1. Okay. This is my edge set. Edge set is determined by this P. Okay, how do I determine my edge set? I put all pairs I comma j. I is not equal to j, so it's undirected. Okay, I'll put it here, undirected, if it's not obvious. It's undirected. So I take any pair xij, any ij, I put them if xij is equal to 1. And what is xij? It's symmetric. Xij is same as xji, so makes it undirected. Okay. And xij is our IID Bernoulli random variables, P. P comes here. What does it mean to say xij are Bernoulli random variables? Is that the probability xij equal to 1, the probability xij equal to 1 is P, and probability xij equal to 0 is 1 minus P. That is, each xij is a coin. I have a coin for each ij. I toss it. If it is heads, I keep the edge. If it is tails, I delete the edge. Okay, that is what am I doing? In other words, I take a complete graph Kn and delete edges, go to each edge, toss a coin. It comes heads with probability P, tails with probability 1 minus P. If the coin is tails, I delete the edge. And to each edge, I do it independently. Okay. So if you do a very simple computation, what is the probability Gn comma P is equal to a given graph G? You fix me a graph, say, let's say a triangle, let's say some other graph, you fix it. You ask what is the probability G and P is equal to G. Then what happens is that it is P to the power M, where M is the number of edges in the graph, and 1 minus P to the number of edges not present, N choose 2 minus M. Okay. This is my uh, uh, probability for any given graph. Probability, you take a particular graph is realized, or when I delete edges randomly, when I go around madly deleting edges at random, that you see a particular graph G after my procedure is this probability. Trivially, if you put P equal to half, the number of edges do not matter. All the possible graphs take the same value, same probability. That is, you are truly picking a graph uniformly at random. Okay. This was the philosophy of Erdos-Renyi originally, P equal to half. You pick one graph from all possible graphs on n vertices, you pick one uniformly at random. Okay. The number of possible graphs are n choose 2. On a number of possible simple graphs on n vertices is n choose 2. And so if P is equal to half, you get half to the power n choose 2. Okay. There are two beautiful references, very theoretical. Classical random graph reference is a book by Alan Fries and Michael Karonsky. And if you want a very applied perspective, dealing with a whole range of different models, is a very nice 2 volumes by Remco van der Hofstad. Okay, Remco von der Hofstad rather. Okay, so it's available, both are, you can find it online. Remco's is on his webpage, it's very nice. Gives you why random graph theory from the perspective of networks and so on. Okay, and tells you enormously about that Erdos-Renyi graph is, studying Erdos-Renyi graph is just the tip of iceberg as comes to studying random graphs. Okay, now let's do our this thing. To me, I will abbreviate, instead of calling I of G and P, I and P is the edge ideal of a Erdos-Renyi random graph, or to us, this is what I call as random edge ideal. The only model for this talk. So equivalently, what does it mean? Remember, in edge ideal, I'm taking pairs. I have n variables. I'm taking every pair. Edge ideal consists of pairs. Okay, where the pair is determined by the edges. My edges are determined by a probability P. So it means that choose every generator xi, xj with probability P and independently. I have n choose 2 possible generators. Each one of them is chosen with a probability P, else not chosen. Okay, and independently. That is, you go to xi, xj, toss a coin, keep it. If it is heads, if you get tails, you remove it and you generate your edge ideal. So your randomness purely comes because your set of generators is random. That's it. So this is a very simple model of random monomial ideal. Well, the first model anyone would naturally think of, in some sense, a probabilist would think of. And we started studying, and we realized, as I said, we started studying in 2017, and Ehrman and Yang came up with similar thing about it in 2018. They already, we saw their paper, which was of this same nature. Okay, so the degree, important thing, the degree of the generator, as someone asked, is always fixed here, equal to 2, but the number of variable goes to infinity. N is going to infinity, D is always 2. A different model was considered by, if you want to understand the subject, these are three people I strongly recommend look at the papers. They have done a lot more, a lot of interesting stuff. Okay. So D. Laura and others, his co-authors, sorry, his or her, I'm sorry, I do not know. Actually, it's a lady or a guy. Okay. So D. Laura and others have considered, models where the number of variables is fixed, but the degree of generators goes to infinity. Okay. So N is fixed, but D goes to infinity. So a very different model. Okay. And N has to go a little, but it need not, D need not be fixed. Of course, if N is fixed and so on, you can ask. Okay. So they deal with more general models. Okay. I have to be a bit careful with this. I'll just say this. The number of variables is a bit trickier. Okay. So cool thing. Okay. Here is our first result, already pretty striking. Okay. So what do we show? If I consider the probability, my random edge ideal as a linear resolution, it's asymptotically the same as the probability it has linear presentation. And it takes two values in particular, okay, 1 or 0. Okay, it takes the values 1 or 0, depending on whether this n square, 1 minus p square, p goes to 0. Okay, one point if I didn't mention, let me emphasize, or p can be considered as a function of n. Even though I don't write it explicitly always, this is a standard notation in random graph theory. I'm sorry. Whenever I talk to non-random graph theorists, it takes me, you need this thing to understand that people don't realize P here is a function of n. It looks a crazy statement. Okay, and what is this? Absolute is stupid, infinity. Yeah, sorry. Okay. So depending on n square, 1 minus p square p, whether this goes to 0 or infinity, the probability of linear resolution or presentation both converge to the same, 1 or 0. And actually, we say something more. We say something even more. That the probability, this is not just coincidence that the two probabilities are equal. We say something very strongly that if you generate an edge ideal, you pick an edge ideal at random. Suppose your parameter P was chosen such that n square 1 minus p square p converges to either 0 or infinity. That is, it doesn't converge to constant. As you can already see, I'm going to tell you something about constant case as well. Okay, constant case has some complication. It doesn't converge to a constant, converges to 0 or infinity. Okay, that is not a, doesn't converge to a non-degenerate constant. Then if you don't see linear presentation, you cannot see linear resolution. Okay, that is, it has a linear presentation. If you observe linear presentation, that is, if you see it as a linear presentation, it has to have linear resolution. This is a very strong statement. Linear presentation is about 4 co-chordal cycles, things which are local, whereas co-chordal is very global. all cycles of all possible length scales. I'm saying that if you cannot see a 4 co-chordal, if you have 4 co-chordality, you will have co-chordality. Okay. Okay. Now, so this is a fairly strong this thing. So, I mean, essentially what you have is, once I prove the second statement, that linear presentation happens if and only if linear resolution for this case, for this choice of parameters, I need to prove only the first statement for linear presentation. Okay. Because I've shown that if you have linear presentation, you will have linear resolution. And so this is straightforward. Okay. Yeah. Okay. Now, what about the case of constants? If n square 1 minus p converges to some lambda in 0 to infinity, it can occur in two different ways. This is important for us. So, other point, when does this converge to 0? Either when p is going to 0 very fast, or 1 minus p is going to 1 very fast. Sorry, 1 minus p is going to 0 very fast. So this can go to 0 when p is going to 0 or p is going to 1. So it happens at the two extremes. It happens close to 0, close to 1. Okay. And now, when it converges to a constant, and if it's because p is going to 0, if this is converging to constant, p or 1 minus p has to go to 0. Okay, if this is true, either p has to go to 0 or 1 minus p. Let p go to 0. Okay, equivalently p goes to 0, p goes to 1. So let p go to 0. Then the probability of linear resolution and linear presentation, we give you the explicit probabilities. For people who know some probability, this is nothing but a probability of a Poisson random variable being less than equal to 1. Okay, I'm not going to tell you what is a Poisson random variable. Okay, this is nothing but probability a certain Poisson random variable is less than equal to 1. Okay. Okay, so this is the explicit probability. Again, the probabilities are equal. The last one missing case, when this converges to lambda but p is going to 1. Okay, when p is going to 1, in this case, the two probabilities differ. One of them is e to the minus lambda squared by 8. Other is this e to the minus some series, of which lambda squared by 8 is the first term. And more importantly, if lambda is greater than or equal to 1, this is equal to 0. If lambda is greater than or equal to 1, there is linear presentation with a positive probability, but there is no linear resolution. Okay. So this again, the same thing. It's some Poisson random variable having value 0 is e to the minus lambda square by 8. Okay, these are probability mass functions of some random, well-known random variables. Okay. Okay, so I'll quickly say the consequences, and I won't go too much into the proofs. I'll give a more detailed slide. I don't think I have that much time. So, but as you see, we explicitly characterize the probabilities in all the cases. This is the advantage, that you're able to say that, okay, what is the chance that you pick a random ideal out of a box of, I mean, you have a box consisting of edge ideals on n variables. You pick one at random. What is the probability it will have linear presentation but not linear resolution? Okay, what is the chance? Okay, it tells you it's very highly unlikely except in a very specific case. Okay, so what we have said is that linear resolution is same as regularity equal to 2. So what we are saying is regularity is strictly larger than 2 if and only if p is between 1 by n square to 1 minus 1 by n. So 1 by n square, because np square n square p goes to 0. N square p goes to 0 means that p is smaller than 1 over n square. Okay, n into 1 minus p goes to infinity means this. The other way around, p is greater than 1 minus 1 over n. Okay. So in this regime, this will go to infinity. This essentially the where if p is between these two, n square 1 minus p square, p goes to infinity. Okay. And the previous result known was by Erman and Yang, who had this weaker one. As you see, it's weaker. It's already included in our case. Okay. Ours is sharp. Outside this, regularity is equal to 2. Okay. Erman and Yang had this. Okay. So I'll quickly say a word about the proof, one slide. The remaining you can see in the paper, as well as I'll send the authors the updated slides. Okay. Or I can see if at the end someone has an interest, I can explain. So by Froberg's theorem, I know that you have a linear presentation if the complement of the graph is 4-chordal. What is the complement of Erdos-Renyi graph? This is where I need Erdos-Renyi very crucially. What is the complement of an Erdos-Renyi graph? Is the following. If I take complement of an Erdos-Renyi graph with parameter p, it is the set of all deleted edges. An edge is deleted with probability 1 minus p. So very easily, the complement of an Erdos-Renyi graph is nothing but Erdos-Renyi graph with parameter 1 minus p. This is very nice for me, right? I can still use the results on Erdos-Renyi graphs. The complement is not a different class, it's Erdos-Renyi itself. And it is 4-chordal, means that number of 4 cycles in Gn1 minus p without a chord. The number of 4 cycles should be without a chord is 0. The number of 4 cycles without a chord should be 0. There are classical probabilistic bounds called the first moment method, second moment method, which we teach even in first year of B math. I tell students, okay, these bounds, how do you can derive it using very basic probability. And well, it looks like you can make a career out of just applying these bounds. Okay. You should know what to apply to. That's the trick you learn after your PhD and all that. It's not a new bound. As someone said, how far you can go with Cauchy-Schwarz and integration by paths. There is a book saying that how far can you go with Cauchy-Schwarz and integration by paths. Maybe someone can write a book, how far you can go with first moment and second moment bounds. Okay. So the first moment bound says the probability a random variable is greater than 1 is bounded above by expectation, the Markov's inequality. Now a second moment bound says that the probability it is being greater than 1 is lower bounded. So you have an upper bound for this, a lower bound for this, complement of this event. I want to understand when is this 0. I have upper and lower bounds for this using this, 1 minus of it. Now the proof is all by showing that, in the corresponding parametric regimes, this goes to 0, 1, this goes to 1 in one case, this goes to 0. Okay. And this gives me the upper and lower bounds. And it's a probability. So there is always a upper and lower bound for a probability, right? I mean, this is low. Have the trivial upper and lower bounds. So if you show this goes to 0, if I show this goes to 0, I'm done. If I show this goes to 1, I'm done. Okay, this is what we do. Okay, this involves, it's not too hard to guess it. Why I would guess it, you can see from the next. I'm not going to say anything much about this. Okay, I'm skipping over it. Sorry about this. Okay. So the only point I'll emphasize is no linear resolution is similar. Instead of C4 star, I have to look at CK star for all K. So the upper bound is summation of expectation, ECK star. By the way, E is expectation, sorry. Again, talking in two different communities. Okay, expectation. Okay, it's the expected number of such cycles. So as I said, this is essentially what I explained. And I've explained in brief the computation of EC4 star from where you can guess this regime. Okay. The final thing, again, I will skip a little, is that in these two cases, the constant cases, there are well-known results that tell you how many edges are present. When this case, the only possibilities you can have only edges, no triangles, nothing else. So in this case, the edges, I know what happens to edges, and edges are disjoint. That is, there are no triangles. No two edges can be connected. So I have disjoint edges. So I know the structure of the graph. I know the structure of the graph. Okay, I can use the structure of the graph to compute everything explicitly. Same happens here as well. I know the structure of the graph itself. Okay, I know the structure of the graph in this case. I know the structure. I can use this. Okay, I'm recollecting our results to make a point, because I made this point that what our results imply is that regularity is greater than 2 in this case. So it is greater than 2. Herman and Yang showed a bit more. They said regularity is greater than S plus 2 whenever P goes to 0 and P is greater than 1 by NO 1 over S. So this is precisely what tells you here. Okay. What we show is something very specific. We improve. Okay, it gives you a lower bound, but can I give you a correct bound? Is S plus 2 correct? So it says that regularity is greater than 2 when P is like larger than 1 over N. P is going to 0 faster than 1 over N. And below 1 over N square, regularity is equal to 2. In between, do I know anything? We show a very specific case. If P is lambda by N, exactly 1 over N, P is 1 over N, then lambda is in 0 to infinity constant. Regularity minus its expectation, regularity minus the expectation converges almost surely to 0 as N goes to infinity. All the limits are in N. This converges to 0. And you can derive upper and lower bounds for this ratio. Okay, so this limit is non-trivial. That it's not like, I'm taking something which is going like square root of N dividing by N and getting a 0. No. This expectation has a lim sup and lim inf are bounded away from 0 and infinity. Okay. So the infinity part is clear, but it's also bounded away from 0. Okay, we don't have, the missing part is that I don't have explicit limits except in one case. I'm not going to say anything about the proof of this statement. It follows by two things. What is known as a bounded difference inequality. This is the probabilistic ingredient. It's a very powerful inequality due to McDiarmid. And the property we need of regularity from edge ideals is that if you add one vertex, I take an edge ideal, I introduce a new variable and some new edges also. Okay, I introduce one new variable and some new edges. Or let's say I delete all the edges on a variable. So suppose I delete all the edges incident on a variable. How does the regularity change? Vertex Lipschitz means that regularity changes by at most 1. Okay, that's what vertex Lipschitz. The regularity changes at most by 1 if you delete a variable, okay, in your edge ideal. The stronger property we prove, I will stop with explaining this alone and make one more remark, sorry. Regularity scaled by n when lambda is less than equal to n, remember this parameter, converges, I know now explicitly the limit. I'm going to explain you what all these terms mean. Okay, what does it mean to say induced? I mean, what is new? What is this? This GW lambda is a random graph, a random tree. It's a random tree. I'm going to explain what is it. This is the cardinality of the vertex set. Okay. So firstly, what is nu of G? It's the maximum induced matching of G. We know what is a matching. Okay. It is a matching such that I view the matching as a subgraph, it's induced subgraph. Okay. That is, if I have two edges in the matching, it is not possible to have an edge between any of the vertices in the edge matching. Okay. So that is, there is no edge between two edges, any two edges in the matching. That is an induced matching. And you look at the maximum one. Among all possible, instead of knowing the maximum matching, I look at the maximum induced matching. This is new of this. Okay. And simple example, if I take a 4 cycle, maximum matching is cardinality 2, maximum induced matching is cardinality 1. I cannot have an induced matching on 2 with 2 edges, because the moment you put one more edge, there is an edge here. Okay. So this is what happens. You cannot have a maximum induced matching of 2. What is GW lambda? It is nothing but what is called the Galton-Watson tree in probability, very probabilistic object, which was studied by Galton and Watson in 1870s to understand how do English families or surnames, do they survive or not? Okay, survival of English surnames or genealogies. Okay, some people think it has a very racist origin, but anyway, it's nothing can be done now. So, our classist origins. What is this tree? I take one vertex. To each vertex, I put a random number of children. And then to each child, I put another random number of child. Okay. To every vertex, I put another random number of vertices more. Okay. And I keep doing this. I build my tree. And all the randoms are Poisson lambda random variables. So can I take a couple more minutes and just complete?
Yeah, sure.
Yeah. Okay. So this is the point. This is my random tree. Very simple. To each vertex, a tree has only a forward direction. I can start from one vertex, look at its neighbors, further neighbors, no cycles. So at every time, the number of new neighbors is a Poisson and all are independent. This is the Galton-Watson tree. So what have we shown is that regularity for lambda less than equal to 1 and p is lambda by n. Regularity divided by n converges to the induced matching number, okay, of this probabilistic object, of this random tree. Realize two things. One is that it's a tree, not anymore a graph with cycles. There are no cycles in the limit. I have to compute induced matching number of this. There is more hope of computing it explicitly. Okay. And the proof, very interesting. This is unfortunately, I'm not able to describe more, sorry. First is the algebraic result, a combinatorial commutative algebra. Regularity minus 1 is the induced matching number if G is a forest. This is why I've converted a question about regularity, which is very complicated looking, to a question of induced matching number. Then there is a very beautiful theory called Benjamini-Schramm convergence or local weak convergence, which tells you if you look at a finite fixed neighborhood of a vertex in the Erdos-Renyi graph, it looks like a fixed neighborhood in the Galton-Watson tree. It looks like a tree. The Erdos-Renyi graph looks like a tree. And then here is where I need lambda less than 1. The tree is finite. The tree cannot be infinite. Okay. So these are three things you have to put together correctly. It's not a big deal to put together once you know these facts. Okay. But it's a very beautiful thing. It relates. Whenever I have these two properties for my graph, the proof can be carried out. I mean, this proof can be done for more general random graphs than Erdos-Renyi. The first theorem needed Erdos-Renyi. This one doesn't. This is known in more generality. This is known in more generality. But lambda less than 1 is a very annoying assumption. We would like to remove it. I will say the last point. I will make one remark. What Arindam introduced yesterday, what is called Cohen-Macaulay. The point was that there are a lot of conjectures saying that random monomial ideals are rarely having Cohen-Macaulay. Deal, Laura, and others stated conjectures and some theorems that random monomial ideals do not have Cohen-Macaulay. Cohen-Macaulay implies unmixedness, and unmixedness is characterized in very graph-theoretic terms that every minimal vertex cover has same size. Okay, and I will say, I mean, you can find the definition is that Vertex cover is, of course, I assume all combinatorialists know. And here is the last slide I will stop with. I'm not going to say, sorry to the organizers. I will end on a very cynical note. Picked up the cynicism, you can blame it on Arindam, who pointed out this quote yesterday to me. Mike Hotster, life is worth living in Cohen-Macaulay rings. D. Laura, others showed us random monomial alleles are rarely Cohen-Macaulay. And what we show is not alone you are rarely Cohen-Macaulay, you are rarely unmixed too. Okay, so put all the three together, life is rarely worth living. Okay, thanks a lot.
That was wonderful. Okay, so
Yeah.
do we have any questions from the audience or, or any comment? So these last 1 hour were worth, very worth. So yeah, I have one. So
Yeah.
when you said uh, four co-chordal implies that it has a linear presentation, something, or maybe it's like more algebraic. So does it like suppose we have four co-chordal as well as five co-chordal? Does it say that the second map is also linear or something? Because
Okay, this Arindam, I would ask Arindam to answer.
yeah. So
It's slightly more complicated than that actually. So, so just to make it easy, so what happened is up. Yes, there is a characterization for up to a certain point. It is co-chordal. So okay. So if it is 4 and 5, it's just the D1 and D2 are co-chordal, are linear.
oh, so it goes the number ways. If I suppose say 4, 5, 6, so it will be like up to third map they will be linear.
Yeah.
Okay. That's great. Yeah.
Okay.
So one more question I have.
Yeah.
So four co-chordal implies four co-chordal is almost always co-chordal. That's what you showed.
Yeah.
So is there anything to do with four, or like it's just any number you choose and say k co-chordal is co-chordal almost always?
No,
No. Okay.
because lower, right? I mean, the issue is that
Sorry to
you have
interrupt.
to assume 4 to k, which is a stronger than 4. So you can have k co-chordal maybe, but may not be lower.
Yogesh, I have a point to make. Is that okay?
Huh? Yeah, please.
Yeah. So, Justine, to answer the last question, honestly, I exactly don't remember the statement. I think the answer is something like this. It is K co-chordal if there is no induced cycle greater than equal to length K plus 3 or something like that in the complement.
Okay.
Yeah. So there is a paper by Eisenbud, Hulek, Popescu, which is something like linear resolution and NP, something like NP resolution or something. If you search Eisenbud, Hulek, Popescu, that's the I'll just write the name. That paper gives you the complete characterization. Eisenbud,
Okay.
Hulek.
No, my question here was just for a particular cycle. So in these observations, what we saw is like there is no four cycle in the chordal graph in the complement of the graph. So we
Yeah.
call it four co-chordal. So in this sense, if I define a k co-chordal or something like the complement doesn't have a k cycle, induced k cycle.
Only
K
okay.
induced.
Only K cycle. No, that doesn't say anything.
So you have to assume from 4 to k, up to
Yeah,
k.
something like that.
So
But that
will
is
be very
already you
strong.
have
Yeah.
taken
That
4
is
a,
that
4
is very
entire.
strong. Yeah, definitely.
That is very strong. Okay.
Yeah. Okay.
Yeah.
Sorry to.
4 very special is that it's, among this class of co-chordality, the simplest is 4.
Yes.
So what we are saying is that if you cannot get 4, if you cannot find if you manage to get 4 co-chordality, or rather if you see what we have shown is that if you have a 4 cycle, okay, which has no chord, if you have a 4 cycle if you cannot get a 4 cycle without a chord, you cannot find higher cycles without a chord. So if you want to find a cycle, invert the question, you want to find a cycle without a chord. All we are saying is that if you cannot find one with 4, it's harder to do it with higher also. Okay.
Yeah, thank you. Yeah.
I
So do
think
we have any?
this has nothing to do with probability. Like when
No,
you are,
this is purely probabilistic. It cannot happen in
yeah,
general graphs.
yeah,
It's very much to do with Erdos-Renyi graphs that somehow that this is a very common phenomenon in very probabilistic things, and this is why random graphs are so useful. Is that once you rule out certain the probabilistically the most simple things are more the most simplest obstructions are the ones that are more likely to occur. If the simplest way to have something occurring is ruled out, the
yeah,
complicated things cannot occur. Okay. Like for example, the most famous theorem of Erdos and Renyi, goes back to Erdos-Renyi. Who formalized it, I do not know, but observed by Erdos-Renyi first itself in random graph. And if you take a random graph, if it does not have an isolated vertex, if an Erdos-Renyi random graph does not have an isolated vertex, okay, the graph will be connected.
yes, yes.
Okay. This is one of the most famous theorems in this field. Okay, so people from this drives the entire heuristic that the simplest way for a graph to be disconnected is to have an isolated vertex. Okay, this is the simplest way the graph can be disconnected. You have one isolated vertex, simplest structure. And Erdos-Renyi said if this simplest thing cannot occur, you cannot have more complicated obstacles to connectivity. And what we are saying here is the simplest obstacle to chordality is to have a 4 cycle without a chord. Simplest obstacle to chordality is a 4 cycle without a chord. And all we are saying is that if this does not occur, okay, you cannot have more complicated obstacles. Okay. And this is exactly why I told that once Arindam told me this, I said immediately this has to be true.
Thank you.
Yeah. So do we have any more questions from the audience? So if not, let's just unmute ourselves and thank our speaker. Thank you, Yogeshwaran, for this
Yeah,
wonderful
thanks a
talk.
lot. Yeah.
So this slides and recording of the talk will be available on the website for the later use if you want to go back and see anything.
Yeah. I'll send you the updated slides now. Okay.
Yeah, so I'll update it.
Some proof details and stuff, are there, and some extra things. The precise statement of life not worth living mostly is also there. Okay. So I'll just send it to you, and then you can put that up. Okay.
Yeah, thanks. Yeah, so I'll update it on web page so you can go and check it over there. Uh, the next talk we have is on Tuesday, next Wednesday, sorry, at 11 o'clock. The speaker for the next talk is Manisha Benzola. See you guys next week, Wednesday again. And thanks for